Okay, good afternoon, good morning, good evening, wherever you are in the world. I would like to welcome you to this keynote talk, to today's keynote talk, which Laurie Lamel and myself will chair. The keynote speaker for today is Pascale Fung. She has affiliations with the Department of Electronic and Computer Engineering and Computer Science and Engineering at the Hong Kong University of Science and Technology. She's also active in computational linguistics and has been awarded there, elected fellow for significant contributions to statistical NLP. And she's working on human-computer interaction. And why we invited her here to Interspeech is because of her work on ethical and technological challenges of conversational AI. And we are very happy to watch a video from Pascale because she couldn't make it here for obvious reasons. And after that, we will have some time for questions, not too much time. So I will keep it short here and would like to ask the video to take over for the presentation of the talk. Thank you very much.
Hello, everyone. Thank you for coming to listen to my keynote on the ethical and technological challenges of conversational AI. I'm Pascale Fung of the Hong Kong University of Science and Technology. These slides are prepared with my students, Zhao Jiangling and Andrea Madotto. I'm also director of the Center for AI Research at HKUST. These are some of the recent keynotes that have covered many technological and ethical issues of general conversational AI systems. So in my talk today, I will focus on the challenges of sequence-to-sequence neural conversational AI systems. And I recommend you to look up these other keynotes for other areas. So these are some of my students who have contributed to the work, some of the work I'm presenting today. And this is outlined on my talk. Conversational AI systems have many industrial applications. We have seen them for many years, including Apple Siri, Google Assistant, Amazon Alexa. In our team, we also came out with MooBox, and more recently, Nora Quarantine Health Assistant. There are many complex tasks that require multi-turn conversations, such as for restaurant booking, movie recommendation, or virtual therapists. And they require both chit-chat and task-oriented skills. So we can see the need of having a more versatile conversational AI system that has all these important skills. And many of these are ongoing research problems. Dialogue systems or conversational AI systems are typically divided into two categories. One is open domain chit-chat. The other one is called task-oriented dialogue system, which is designed to help users accomplish certain tasks. In terms of implementation, most of the commercial task-oriented dialogue systems are modularized. This is the architecture of modularized task-oriented dialogue system, which have been in existence since the early 90s for about 30 years now. This kind of architecture typically consists of 4 modules. From user input, we will get semantic decoding. There's a dialogue manager that tracks dialogue state and access an external knowledge base. And with dialogue policy, it will generate machine response. And then usually there's a natural language generation module that outputs the response to the user. This is basically a speech cycle. These kind of systems are known to be stable, so that's why they're widely used in commercial systems. However, they require extensive labels to train each of the modules. These systems require considerable, These systems require considerable human labor to train each of the modules. And training these modules separately will also make the final performance suboptimal. For open domain Chit-Chat dialogue systems, there have been mainly 3 different approaches. The first is enabled by a set of pre-designed if-else rules. So this is more or less like an expert system. Retrieval-based approach is the second one. It uses dialogue context as query to retrieve the next response from a set of predefined response candidates. More recently, neural sequence-to-sequence dialogue models generate response token by token using maximum conditional probability. And it gives better domain generalization, requires little human intervention compared to the rule-based and retrieval-based methods. Therefore, in this presentation, we will focus on end-to-end generation-based methods for conversational AI. Here's a brief history of neural conversational AI. The first papers on neural conversational AI appeared in 2015 to 2016, starting with sequence-to-sequence generative dialogue models for simple chit-chat. In 2016, Jiwei Li et al. Proposed persona-based conversational model to make the chit-chat model more consistent. At the same time, people started to explore task-oriented dialogue in a neural setting, either in a retrieval approach or optimize the dialogue policy in an end-to-end pipeline setting. More recent work started in 2019, such as Transfo, and Hello GPT-2, leverage the success of pre-trained, large-scale pre-trained language models for training personalized and task-oriented dialogue models. So what kind of neural conversational AI systems are we talking about? To build a basic vanilla sequence-to-sequence conversational AI system, there are essentially these 5 simple steps. 1, you choose a training data set of human-to-human conversations without any label. 2, we choose a sequence-to-sequence model. Today, we mostly prefer using large-scale pre-trained language models. 3, we train the model with supervised learning or fine-tuning. And finally, we evaluate the model with either automatic metrics or human evaluations. Let's take a look. Let's start with data set. Here we have this data set of human-to-human dialogue. And here's a list on the right-hand side of 5 such data sets. They're usually pre-processed to have only 2 speakers and usually no more than 2 turns. So some existing data sets are being used to train the model to imitate the system response. For example, Daily Dialogue contains data from various websites which serve for English learners to practice English dialogue. Ubuntu Dialogue, Twitter, or Reddit are conversations from forums. Open subtitles are crawled from movie and TV subtitles. For a vanilla sec-to-sec system, there are 2 families of generative models that can be used. One is an encoder-decoder architecture where the dialogue history goes into an encoder and the response comes from the decoder. 2, there is a causal decoder where both the dialogue history and response are input similar to a language model. Conventionally, the most popular has been the encoder-decoder architecture. And then Hugging Face proposed a decoder-only model, which can be considered as a encoder-decoder architecture where the parameters are shared between the encoder and decoder. There are pros and cons to each of these 2 approaches we will discuss, but in general, there's not a clear winner. So for training in general, we use maximum likelihood estimation in supervised learning. Independently of which architecture the model is trained using the goal response provided in the data set. The output of the model is a probability distribution over vocabulary. And if we use greedy decoding, the model will output a token with the highest probability. So the model is trained to maximize the probability of the target sequence tokens. Multiplying probability may lead to numerical instability. Therefore, we use the sum of the log probability. This becomes a loss for the model which is a cross-entropy loss. After the model is trained, we will use it to generate responses. Here we describe the greedy decoding with argument max at each time frame. We start the decoding by providing to the model a start of string token. The model then generates a distribution of the vocabulary, a vector of dimension 1 times the vocabulary size. Then we choose the token with the maximum probability, or argmax, over this distribution. This is the greedy step. The output will be a token. Here is how in the example. We repeat the process until the model generates a end of string token. Notice here we are describing the decoding process. The model can be both encoder, decoder, or decoder-only architecture. This is to say that the decoding process is more agnostic, more model agnostic. And then we need to evaluate our dialogue system performance. We can use either automatic evaluation or human evaluation. Automatic evaluation compares machine-generated responses with human responses in terms of perplexity, n-gram overlapping, and so on. Recently, neural-based methods also have been proposed to learn human standard evaluation. Human evaluation can be divided into 2 subcategories, namely static human evaluation, which compares the responses generated by different models, or in a dynamic evaluation where the human evaluator is also a human user of the system who interacts with these models and give a rating afterwards. So what are the technical challenges of this type of neural conversational AI we're facing today? There are many limitations. In this talk, I will briefly go through these technical challenges, ranging from a lack of diversity to learning to controllability and evaluation and so on. Here, we find that since the seg-to-seg model generates automatically token by token, it kind of generates responses that do not have a lot of diversity. For example, here, what are you doing today? Human asks, system says, I don't know. What is your name? I don't know. What is your favorite food? I don't know. So we can see that this kind of architecture, since it was trained with maximum likely loss or maximum entropy loss, it might generate repetitive responses because it falls into a local minimum and always generates the highest frequency response from the training set. And that can be quite boring and repetitive. This kind of vanilla seg-to-seg model is too weak in terms of parameters. It does not have enough capacity to capture the one-to-many relation between dialogue context and response. However, we'll see that large conversational models such as Dialog GPT somehow helps us to mitigate this problem. So there are many existing solutions for diversifying dialogue responses, including 1, training and decoding strategy. We can use maximum mutual information objective function. Instead of only maximizing the probability of target response given dialogue context, MMI will jointly maximize the probability of T given S and S given T. In the decoding time in practice, the model will first sample the n best sequences according to the probability of T given S, then re-rank responses with the probability of S given T. In terms of model architecture, conditional variational autoencoder is also a good solution, given a dialogue context S. CVAE first samples the latent variable Z according to a dialogue context S. Then it will generate the response by conditioning on dialogue context and the latent variable. The third solution is more data and to use more data and larger model. For example, to use a large-scale pre-trained language model. And the fourth is decoding strategies such as top K or Nucleus sampling. So Vanilla encoder-decoder trained on small conversational corpus are not very efficient as they overfit easily on the training set, and the generator response can be repetitive and not very grammatical. So the solution is to pre-train the model first, and then use it as an initialization for the task. There are different pre-training strategies. The first is to pre-train on a large-scale web text, such as Common Crawl, for example, BART and TFAT model, and for example, Mina and BlenderBot are also pre-trained with massive conversational data. However, we are aware now that there are ethical challenges to using these large-scale pre-trained language models, as we will see later in my talk. Nevertheless, language models such as GPT-2 and 3 and Dialog GPT are good initialization for causal decoder. They are unidirectional language model that pre-train in autoregressive way, GPT-2 and Dialog GPT. GPT-2 is trained on general text, and Dialog GPT is trained with massive dialog data. You can do both. Beam search and greedy search decoding strategy also produce repetitive responses in open domain conversation. And we have seen a paper from Washington U and showing this plot. It illustrates that humans tend to generate more surprising text with fluctuating probabilities than systems. So low perplexity is not necessarily the way human generates tokens or sentences. So this Washington University team then proposed a Nucleus sampling technique to sample candidate words from top N ranked words whose accumulative probability is above a certain threshold, instead of just always choosing the top one. Another challenge is a lack of consistency. Here, human, where were you born? System, I was born in Canada. Human, where are you from? England. You? Where did you grow up? I grew up in Texas. So you can see the machine response is all over the place and inconsistent. This is because these models were trained from large databases that have inconsistent data from different speakers with different personalities and preferences, demographics. So when the model is trained this way, it will have utterances from so many different speakers that it does not keep track. So it can contain attributes from many different speakers, and it does not have consistency. So we can personalize a conversational AI system as a strategy. This can be done we can personalize conversational AI systems by, we can enhance the consistency of conversational AI systems by personalizing them. This can be done in multiple ways. By learning speaker embeddings, which is a feature vector that represents a speaker with attributes, or by providing a persona description as part of the input of the dialog model. In both cases, specific data sets are needed for the task. So these data sets include persona attributes such as name, address, preferences, etc. Here is an example of the data set being used to personalize a conversational agent. The persona information from human 2 are, I like to ski, I'm 25 years old. Then the dialogue begins by human 1 saying, hi, what do you do in your free time? Human 2, I enjoy going to the mountain and skiing. Human 1, that's cool, you should be young and strong for this activity. Human 2, oh yeah, I'm 25. As we can see, human 2 recalls information from the persona description, and the response of the human is more consistent. So this data set, this kind of data set can be used to train a more consistent dialogue system. And they can be collected by randomly pairing any two annotators and to assign each of them a persona. And then the annotators are instructed to talk to each other, and they will provide persona information during the conversation. This data set can be used to train conversational models that generates a consistent response, as we have seen. Another way to promising way to approach personalized dialogue modeling is via transfer learning. This particular work, Transfo, uses a pre-trained language model GPT and fine-tune it to the personalized data set previously described. From the picture, we can see that the persona information, the dialogue history, and response are all formulated as a single sequence. The model is trained to generate a system response by conditioning on persona and dialogue history. The segment embedding is also used to inform the model of which part of the input belongs to the persona description, which to the dialogue history, and which to the response. Blue is the persona info, pink is history, and green is reply. The segment embedding is summed up with positional embedding and word embeddings, and they become the actual input for the transformer model. The resulting model is able to condition its responses on different personas. This means that given a dialogue history and persona, the model will reflect the persona provided. Other than encoding the explicit persona description, a speaker model uses the speaker embeddings to implicitly encode the persona information. This is another way. This model is trained on the Twitter persona dataset, which consists of a set of conversations from 74,000 users. Each user in the dataset has one unique speaker embedding, which encodes the persona information. These embeddings are then concatenated with a word embedding as the input to the decoder during training and inference. The third challenge of neural conversational AI model or seg-to-seg model is the lack of knowledge. In the previous modular models, modular task-oriented dialogue systems, it was pretty easy to access external knowledge. But in the seg-to-seg model, as it learns from conversations between humans, there's no explicit way of encoding this knowledge. So for example, here, human asks, what is the weather like, system? I don't know. Human, I'm going out to Taylor Swift's concert today. I hope the weather is good. Who is Taylor Swift? The system asks. Okay, never mind. The system doesn't know who Taylor Swift is, but this knowledge can be actually found on the Wikipedia page. So if we train the model with only human-to-human conversation, we cannot incorporate such knowledge. Ideally, we need to design a way to align this external knowledge to dialogue. There are 4 types of knowledge, and our system needs to learn to incorporate them. The textual knowledge, such as Wikipedia articles or online news. The second one is knowledge graph, such as knowledge graph that store relationship between movies and directors. The third one is tabular knowledge, which can be an SQL table, dialog ontology, or any Excel file. And last but not the least is service API. Our system needs to access online service APIs, for example, restaurant booking. And this kind of seg-to-seg model needs to have a way of incorporating all these data, all this structured knowledge. Another challenge is controllability. This is perhaps one of the most important challenges. Here, the model receives as input a very open utterance. Hi, how are you? The model can respond in many different ways, such as I'm good, thanks. I had a really bad day. I'm okay. How was your day? I'm okay. I just finished my training session in the swimming pool. The open domain Chit-Chat systems that are based on end-to-end neural approach, usually it would generate this response token by token. And we have no idea to predict what it will generate. because this model does not have direct control over which response style or topic to use at each point of the conversation. For example, we would like to have a more cheerful or more engaging response, even one that changes topic frequently. That's a desirable feature. More importantly, again, I would like to point out that this lack of controllability also leads to ethical issues downstream, and it might potentially lead to toxic or other inappropriate responses. So large conversational language models such as Dialog GPT, Mina, BlenderBot are very good at conducting conversations with humans in a very fluent human-like fashion. However, one of the main problems of these models is the lack of control over response style, topics, repetition. It is very important for us to assert control to ensure the model will follow a certain topic style and also to prevent inappropriate responses. For example, we might want the model to be tuned to be more engaging by proactively asking questions to the user. We again do not want the model to generate inappropriate responses. So to solve this lack of controllability, there are 4 approaches. Briefly, I'll name them here. Low-level attribute control via conditional training and weight decoding. Control by fine-tuning on style specific data sets. Or model perturbation control by using PPLM and residual adapters. Or control by conditional generation, retrieve and redefine, again, using PPLM and CTRL. Another challenge is that the vanilla seg-to-seg models, since they were invented for open chit-chat and they are often used one turn at a time, it is very natural that they're used only for human-to-machine chit-chat only, one turn at a time. However, task-oriented dialogue systems need to answer user queries with specific knowledge-grounded responses. They need to be both controllable and to interface with external knowledge base and generate API calls, and they might need to prompt the user for further clarification. All this cannot be implemented in an obvious way with the vanilla seg-to-seg model architecture. Multiple modules of task-oriented dialogue systems such as NLU, DST, DP, and NLG must be integrated in a single generative model. How can we do that? How can we make our system more versatile? One of the approaches we proposed back in 2019 was called attention over parameters, where each dialogue skill is encoded with a set of specific parameters. Once this model learns each of the domain or skills independently, then we train a composer model that learns how to select and mix the multiple decoders. This allows for controlling which dialogue skills needs to be triggered given a certain dialogue history. For example, if the model needs to generate a booking API call under the hotel domain, then the composer will mix the hotel decoder with the booking API decoder. For mixing multiple decoders, here we proposed 2 options with attention over the representation, aka mixture of experts, and attention over parameters here. More recently, similar to attention over parameters, we propose a adapter bot to combine multiple dialogue skills into a single versatile conversational model. The adapter bot uses a fixed backbone conversational model, such as Dialog GPT, shown in gray in the figure. Then it learns each dialogue skill using independently trained residual adapters, shown in the figure as adapter layers, with the POS, which stands for a positive response, highlighted. Depending on the skill, the model can process multiple knowledge types, such as text, tables, and graphs, shown as meta in red in the figure. Finally, a skill manager, which is a BERT model, here is trained to select the most appropriate adapter, and which correspond to each skill based on the current dialogue history, again shown in yellow here. Another technical challenge is learning. Learning directly from conversing with a human is a grand challenge for conversational models. Even the most powerful language model cannot learn directly from just directly interacting with humans. These three papers showed us how to learn directly from human interactions by a reward signal and transform it into a meaningful update for the model. However, challenges remain as to how we can extend from this toy data set and model and scale to new domains and in the future. So this is a future work. Another challenge is learning zero-shot and few-shot learning, since collecting database is very laborious and costly, and designing model to be less data intensive is crucial. So far, there have been few work that have been presented, and the performance of a few-shot learning are far from that of a full-shot, fully trained model still. So here's two approaches I've listed here: zero-shot learning and few-shot learning. Another challenge is lifelong learning. Lifelong learning in dialogue is a relatively unexplored area. It usually refers to, for users, for example, the user speaks with the system more, the system becomes knowledgeable more about the user. This requires a way to extract attributes from the previous conversation and remember it and reuse it, for example, as we've shown in the example here. It is challenging how we can use information it has learned from user attributes. Another meaning of continual learning in a dialogue system or conversational AI system is to add new domain or dialogue skills to an existing model without forgetting previously learned skills. And of course, ideally, a conversational AI system should be able to talk and then should be able to see at the same time. It should also be able to learn in a multimodal setting. So here is an example from image chat. Speaker A and speaker B are talking to each other by looking at an image. On the right-hand side, we show a list of data sets for learning a multimodal conversational agent. This is still a very new area in conversational AI. One of the final challenges we're still facing is evaluation. Having a general and automatic way to evaluate dialogue system is crucial and difficult still. Perplexity has been found to positively correlate with interactive human judgments. So here, from the figure on the top, x-axis is the perplexity and y-axis is the interactive human evaluation score. It has been shown that the lower the perplexity, the higher human evaluation score. Mina, for example, is very close to human score. This is actually very neat because perplexity is a metric of confidence over the generated response. On the other hand, as I have mentioned earlier in my talk, some follow-up work show that if the perplexity is too low, the human evaluation score decreases. So human answers are not strictly low perplexity in reality. So in general, learning a good evaluation model is as hard as learning the dialogue system itself. It's a chicken and egg problem. It is still unclear how general this scoring model and metric are. And if we have a perfect evaluation metric, we should also have a perfect response score. So therefore, a perfect conversational AI system. So this is kind of open research. Conversational AI systems learn from human-to-human conversations and consequently pose ethical challenges in several ways. More importantly, large-scale pre-trained language models are providing diversity and fluency to ConvAI systems, but as a black box have inherent challenges in ethics. These are some of the ethical challenges in specifically in neuro-conversational AI, but in general also apply to conversational AI systems in other approaches. Namely, they will generate emotionally insensitive responses, inappropriate responses, unconscious bias responses, political sensitivity, and also their response can be in violation of privacy and security. So how can we mitigate this? Set-to-sect models and some other models for conversational AI do not have a mechanism for understanding emotion, and they do not know how to respond in an emotional manner, which is important for an engaging conversation. The set-to-sect model just maps input to output, and it cannot be forced to be empathetic. The data set often does not have dialogues in which the system responds in an empathetic way. Here, both data annotated with the emotional label and specific models for empathy are needed. So there are two lines of work to mitigate this. The first one generates the emotional response according to a preset emotion. This line of work, such as Emoji Talk, emotional chatting machine, and so on, they assume that the generation is conditioned on a given emotion label. However, we often do not know which emotion is appropriate in order to generate an empathetic response. So the second line of work jointly learns the user emotion recognition and corresponding empathetic response from data. So we'll focus on this second line of work here. So to be empathetic, the model needs to understand the feelings of the conversation partner and reply accordingly. For example, when the speaker said that his or her son got promoted, instead of asking why he got promoted, saying congratulations to the user will make the conversation more engaging. Empathetic dialogue here from Facebook is a good data set for modeling empathy. It has it has human labels on the emotion of the utterances. The data set provides a situation that a speaker currently is facing and the emotion label of the speaker. The listener needs to understand speaker's emotion and reply accordingly. A common way for modeling empathy is learning emotion recognition and response generation jointly. This is also our approach in a system we name CARE, the empathetic chatbot. MOO here by our team first captures the user emotion and outputs an emotion distribution. Based on this, MOO will softly combine the output states of the appropriate listeners, which are each optimized to react to certain emotions, and then it will generate an empathetic response. This way, MOO selects the correct listener according to the user emotion in order to make the response more empathetic. Emo-Prepend uses a pre-trained emotion classifier to classify the user emotion and uses the predicted emotion label as additional input to the model and generates the response. Our CareBot, on the other hand, uses fine-tuning on the GPT model and fine-tune it on the empathetic dialogue dataset with 3 learning objectives. One is the pseudo task of emotion detection, and the other 2 are response generation and sentence selection. Here comes the perhaps one of the most discussed ethical challenge of conversational AI systems. Generative conversational models that were trained on internet or social media data might give inappropriate responses. In the first example, the system is encouraging the user to commit suicide. In the second example, when the user asks about favorite food, the system replies that it likes cocaine or drug. In the license example, the response is outright sexist. The system basically learned this kind of inappropriate, toxic, biased response from a pre-trained model trained on a large internet database. It is very important for us to mitigate these inappropriate responses to avoid harmful consequences. So this is a way we need to basically guarantee safe conversational AI. The first step towards building a safe generative conversational model is to filter out the inappropriate response during data preprocessing stage. The filtering methods can be used to train different classifiers to detect toxic and biased content from the training data, or use keyword-based matching to filter out unwanted content from the training data. After the model has been trained, we can also block the n-gram from the predefined sensitive word list during beam search decoding. However, the model can still generate inappropriate response composed entirely of safe words. So what do? After the model generates such responses, we need to have additional safety layers to block the inappropriate responses. These safety layers are classifiers for toxic, biased, unethical content. Once the generated responses are detected as inappropriate, we can either resample a new response or reply with a predefined response. Can we debias and detoxify models themselves? This is an area for ongoing research. Another challenge is when conversational AI systems use unconsciously biased or discriminatory language with polite words. So here, the system responds to a good woman should be set on the pedestal by her man with "I'd rather not be a woman." And another model, when the input is women should be cherished and protected by men, it says, yes, it's our responsibility. So the dialogue system can be very empathetic, agrees with the user, but this is kind of discriminatory nevertheless. So we have designed a way to detect benevolent and hostile stereotypes. And we use these 22 statements from psychology studies to test ConvAI system response. So we consider response bias if the entailment model classifies it as entail and non-biased otherwise. The score is rescaled between 1 to 5 to align with human judgment. So here are some evaluation results of 2 chatbots. We can use this method to evaluate different kind of conversational AI system for unconscious bias. Different companies have different policies regarding the handling of politically sensitive user queries. Here we see a few examples. Currently, the main approach to handling political sensitivity is simply topic avoidance. It's a strategy by changing the topic, simply by changing the topic. And this technique is safe, but it is at the expense of providing engagement. It might turn off some users. Instead, researchers are looking for ways to provide political prudence in conversational AI systems without sacrificing engagement. Now, a system's conduct is considered to be safe if it does not generate offensive, hostile, or toxic response, and neutral if it displays an unbiased stance without showing any partisanship. We propose 3 automatic metrics to measure political prudence in the system. One is hyperpartisanship. It measures the system's degree of political partisanship using a BERT-based binary classifier, fine-tuned on hyperpartisan news classification. Second is a measure of offensiveness to see how the system produces not okay response to send in a friendly conversation with someone you just met online with a offensive classifier. Third is the measure of slantedness to measure whether a system agrees or disagrees to a bias input in the political context. Here we use a pre-trained natural language inference model for assessment. So here we have neural conversational AI systems that are based on large-scale pre-trained language models such as Dialog GPT, Empathetic Bot, Persona Chat. And we compare them to Wikipedia knowledge-grounded chatbots. We proposed previously a Wikipedia adapter of the aforementioned adapter bot and train on wizard of Wikipedia data. And more recently, we used the backbone of a Blender bot, which is a publicly available multi-skill chatbot. We add a safety layer that detects whether the context is politically sensitive or not. When the context is detected as politics, the system will display relevant factual information from Wikipedia instead of providing an evasive answer. So the system has a safety layer specialized for political discussion, as shown here. For example, when user asks about minimum wage, the system says a minimum wage is the lowest remuneration that employers can legally pay their workers, as a definition. And the result of the assessment shows, while we compare Wikipedia knowledge-grounded chatbots to the standard ones based on large-scale pre-trained language models, the assessment results show a tendency for the knowledge-grounded chatbots to be less partisan and also more engaging. It is able to carry out political discussions while staying neutral to biased contexts. One of the issues of ethical challenge of conversational AI system, is in particular neural conversational AI system, is in privacy and security. Conversation applications in healthcare and finance often include sensitive personal identifying information called PIIs. Users mostly do not know how their PII is being used, processed, stored, or shared. Article 32A of the GDPR, for example, requires that personal data needs to be pseudonymized and encrypted. But PIIs in large amounts of data used for pre-trained language models might be impossible to detect and hence not possible to be encrypted or pseudonymized. So here are some examples. GPT-2 memorized some text about, addresses, names, email addresses, and numbers, and so on. Here is an example from the paper by Kalini et al. This year, showing a manual categorization of the 604 categories out of the 1,800 examples, memorized training examples that were extracted from GPT-2. We can see that, in these categories, from news to different web forms, there are a lot of counts of named individuals, contact informations, and a list of numbers such as dates and sequences and so on. So according to many ethical standards, since 2017, we have seen over 100 such standards drafted. Here we list 2 AI ethical standards by 2 governmental bodies. On the left-hand side, we have those principles endorsed by the Chinese National Governance Committee for the New Generation Artificial Intelligence. On the right-hand side are those elaborated by the European High-Level Expert Group on AI. And we can see that many commonalities between these ethical standards highlights importance of fairness and justice, diversity, privacy, and technical robustness and safety, controllability, and so on, covering what we have pointed out so far in terms of ethical challenges in conversational AI systems. So in conclusion, conversational AI systems have become more powerful and human-like thanks to large-scale pre-trained language models. There are many technical challenges that remain. With time, they become ubiquitous in applications. They will be on all the time, and people will be used to talking to them. With great power comes great responsibility. These systems need to respect privacy and security, avoid inappropriate responses, mitigate social bias, and in general, follow ethical standards and regulations. Here are some of the data sources and challenges that are good for